Good morning, Manada. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn some of the definitions and the terminology which we have used in the UHF transmission lines and applications, as in the Module 5 in electromagnetic waves and transmission lines. So definitions and the terminology which we have used in the UHF transmission lines. Where UHF stands for ultra high frequency transmission lines and some of the applications based upon this ultra high frequency transmission lines. Right? So first, what is OC transmission line? OC stands for open circuited. So what is open circuited transmission line? Means when a transmission line is terminated with infinity load impedance. If infinity load impedance means generally we used to consider the notation for load impedance means ZL. If ZL is equal to infinity. Now what is the formula for ZL here means ZL is equal to VL by IL, right? So open circuited, if the load is to be assumed as the current flowing which is through that load element IL is equal to 0, if you are assuming IL is equal to 0, then if you substitute IL by 0 here, then load impedance is, uh, is to be assumed as infinity case, right? When a transmission line is terminated with infinity load impedance, then the line is called as open circuited transmission line, right? So these are all the different cases we have analyzed in the theoretical classes as related to the impedance matching of a transmission line. So in order to know this open circuited transmission line and the short circuited transmission lines, we use the notation for input impedance of a high frequency transmission line as Zin. In that we are assuming we substitute ZL by 0, or sometimes if we substitute ZL by infinity, how the open circuited impedance is to be obtained, right? So when a transmission line is terminated with infinity load impedance, means where ZL is need to be assumed as a infinity 1. So if ZL is equal to infinity means it must be assumed the load current which is flows through that load element load impedance term is 0. We are assuming IL is equal to 0, then ZL is equal to infinity. So if ZL is equal to infinity case, the circuit is called or the line is called as the open circuited transmission line, right? So when a transmission line is terminated with infinity load impedance, then the line is said to be open circuited transmission line. Open circuited transmission line. Similarly, next one is what is SC transmission line? So short circuited transmission line. So the opposite to that of this one is short circuited transmission line when the line is terminated with zero load impedance. As we know that load impedance is represented with ZL and it is equal to 0 in the case of short circuited transmission line. So if ZL is equal to 0 case, we are assuming the load voltage which is to be connected at the load side will be assumed as 0. Means here open circuited terminals case, it is to be considered ZL is equal to infinity. Now this is the case, ZL is need to be shorted. Means VL is equal to 0. Here IL is equal to 0. Depending upon that, the two types of transmission lines we have learned in the theoretical classes also, as here OC transmission line and SC transmission lines means open circuited as well as short circuited transmission lines. So if you consider it for open circuited transmission lines, when a transmission line is terminated with infinity load impedance, then the line is said to be open circuited transmission line. And similarly, when the line is terminated with zero load impedance, then the line is said to be short circuited line. Okay, depending upon this, two types of the impedances will be measured. That is, input impedance Zin can be written as root over, that is characteristic impedance Z0, or input impedance of transmission line can be measured as the mathematical formula as Zin or Z0 is becomes ZSC into ZOC equal to, that is input impedance or characteristic impedance of a transmission line, which should be expressed in terms of short circuited or open circuited transmission line, that is given by root over ZSC into ZOC, right? So open circuited transmission lines case, we are assuming ZL is equal to infinity R, and whereas if the short circuited transmission lines case, ZL is assumed to be as 0. Next, what is the use of impedance transformer or impedance matching? So it is also called quarter wave transformer, where impedance transformer is also called as quarter wave transformer. Quarter wave transformer means depending upon the wavelength of the line, we will have three different cases of a uh, transformers. Those are lambda by 2, lambda by 4, and lambda by 8. Different types of wavelengths or lines are there, that is half wavelength line, quarter wavelength line, and eighth wavelength line, where impedance transformer is also called as quarter wave transformer, means that wavelength is given by here lambda by 4, hence it is called as impedance transformer, is also called as quarter wave transformer. It is impedance, it's impedance which inverts impedance low to high or high to low. So how it is to be a quarter wave or inverter means, it acts like the impedance is changing from low to high as well as high to low. For example, a 120 watts load is to be matched to a 75 watts line. The quarter wave transformer must have a Z naught of 95 ohms. Similarly, this 95 watts quarter wave transformer will match a 75 watts of load to a 125 watts of transmission lines. So this we analyzed in the case of different types of wavelengths of a transmission lines. Those are quarter wave length line, half wave length line, and lambda by 8 is said to be eighth wave length line. So depending upon the beta length, transmission line length, we will be considering L value sometimes lambda by 2 or sometimes lambda by 4 or sometimes lambda by 8. And depending upon the phase constant, sometimes it might be defined along with the um, wavelength, it is beta equal to 2 pi by lambda, or wavelength of the wave can be defined as lambda is equal to 2 pi by beta. How this wavelength can be defined means, after every 2 pi radians, the phase is going to change, and the changes are considered to be along with wavelength of that particular one. So lambda is equal to 2 pi by beta. Now from that, beta equal to 2 pi by lambda. Now if you multiply in order to calculate the length of that impedance transformer, we need to multiply beta and L. Then for this quarter wave transformer case, we use the L value as lambda by 4 and beta value as 2 pi by lambda. Then 2 gets cancelled, and 2 gets cancelled. Pi by 2 need to be obtained as the complete length of that beta L. Now, in place of that beta L is substituted in the input impedance of a transmission line's case. Depending upon the wavelength we have used, then we are going to get the impedance, how the impedance need to be matched in different cases. We have analyzed in the case of theoretical lectures also. Right? So, in general, this impedance transformer is also called as quarter wave transformer. This is the case. Wavelength is nothing but length of that wave will be given or considered to be as lambda by 4. Next is, what are the limits of reflection coefficient and VSWR? As we know that reflection coefficient is represented with gamma and VSWR is represented with S, and depending upon this gamma and L, standing wave ratio, then the limits of reflection coefficient is ranging from -1 to 1 or 0 to 1. Reflection coefficient gamma is ranging from 0 to 1, and standing wave ratio S is ranging from 1 to infinity. How these to be varied means, as we know that reflection coefficient gamma can be expressed as S minus 1 by S plus 1, and the reflection coefficient standing wave ratio S is to be expressed in terms of reflection coefficient, means 1 plus gamma by 1 minus gamma. Depending upon this gamma value, we are assuming the limits of the reflection coefficient is ranging from 0 to 1, and the limits of voltage standing wave ratio is nothing but standing wave ratio S is ranging from 1 to infinity. How it will vary 1 to infinity, as well as how this reflection coefficient as varies 0 to 1, means S is equal to, if you consider first gamma value as 0, means S is equal to 1 plus 0 by 1 minus 0, then it becomes 1. Similarly, if you substitute, means if you are assuming first gamma value is equal to 0, then standing wave S becomes 1. Similarly, if you are assuming gamma equal to 1, then S is equal to 1 plus 1 by 1 minus 1. Then in the denominator part, we'll be having the value as 0, and something by 0 becomes infinity. Okay, so this is the way the ranges of reflection coefficient gamma and the standing wave ratio S need to be written. So limits of reflection coefficient is ranging from 0 to 1, and the limits of voltage standing wave ratio S is ranging from 1 to infinity. 0 to 1 as the reflection coefficient, and the standing wave ratio is 1 to infinity. Then define the term insertion loss. So it is the ratio of current flowing in the load without inserting the network to the current flowing in the load with insertion of the network. So how the loss is to be considered? Insertion loss need to be considered. Means by inserting or without inserting, is there exists a difference, then that difference is said to be insertion loss. So it is the ratio of the current flowing in the load without insertion of the network to the current flowing in the load with insertion of the network. Okay, so this is what the definition for insertion loss. Without insertion of the network to the with the current flowing through that load with the insertion of the network is called as insertion loss. So in this we have discussed the limits of the reflection coefficient as well as standing wave ratio. As we know that reflection coefficient is ranging from 0 to 1, and the VSWR, that is voltage standing wave ratio, is represented with S, and it is ranging from 1 to infinity. How it is varies 1 to infinity, just now we have seen according to the formulas, as reflection coefficient gamma in terms of standing wave ratio means gamma equal to S minus 1 by S plus 1, and S is in terms of reflection coefficient gamma means S is equal to 1 plus gamma by 1 minus gamma. So always here reflection coefficient gamma need to be considered as its magnitude form. And insertion loss. So in order to define this insertion loss, we need to consider the ratio as current flowing in the load without inserting the network to the current flowing through the load with insertion of the network is there any differences exist between two, then that is gives us here insertion loss. Next, what is stub matching? A stub can be used to match load impedance to the transmission line characteristic impedance. So now to match the impedance matching, to get the impedance matching means now to know the process of impedance matching means there are two main important reasons for that impedance matching. There is no reflections in that. To avoid the reflections in the in load and source case, and to get the maximum power transfer or to deliver the maximum power transfer, we use impedance matchings. So here stub matching technique is also one of the impedance matching technique, and here stubs can be used to match load impedance to the transmission line characteristic impedance. So if Z0 is equal to ZL case, the line is said to be properly terminated. So the similar case here also, the stubs can be used to match load impedance to the transmission line characteristic impedance. Generally, we used to consider the notation for load impedance as ZL and the characteristic impedance as Z0. If these two are same, then the line is or stub is said to be properly matched. So the stub is positioned at a distance from the load, and this distance is chosen so that at that particular point, the resistive part of the load impedance is made equal to the resistive part of the characteristic impedance, by impedance transformer action of the length of the main line is said to be stub matching. There are two different cases of stub matchings are available depending upon the stubs we are adding. If we are going to add one single stub, then type of matching is said to be single stub matching. Then to avoid the drawbacks which are exist in the single one, then we will go for second type of stub matching technique called double stub matching. Okay, stubs can be used to match load impedance to the transmission line characteristic impedance, and this can be placed or positions at a particular distance from the load, and this distance is chosen so that the particular point is the resistive part of the load impedance is made equal to the resistive part of the characteristic impedance. Then the stub matching is to be formed in that particular case. Next, why a double stub matching preferred over a single stub? So, what are the drawbacks which are exist in the single stub? Why we used to prefer double stub matching? With the help of this double stub matching, we'll be getting maximum impedance matching process. So, single stub matching is useful for a fixed frequency, right? So, single stub matching is useful for a fixed frequency. If you want to go for variable one, we will go for double stub matching, right? So, single stub matching is useful for a fixed frequency. So, as the frequency changes, the location of the single stub will have to be changed, right? So, then next is this is what a point A, a point B. The single stub matching system is based on the measurement of voltage minimum. The single stub matching system is based on the measurement of voltage minimum. Hence, for coaxial line, it is very difficult to get such voltage minimum without using slotted line section. That's why we used to consider, means in order to get variable frequency slots and variable maximum voltage cases, then we used to go for second, or we used to prefer double stub matching over single stub matching. Okay, so the drawback which is exist in the single stub matching is it is fixed, it is applicable for fixed frequencies. If you want to go for variable frequencies, then we used to consider a second type of stub matching technique called double stub matching, right? So single stub matching is useful for a fixed frequency. So it is a frequency, as the frequency changes, the location of a single stub is also going to change. Because of that, we use different slots, and depending upon the stubs we are adding, the second type of stub matching is called as double stub matching. Always we used to add the stub to the nearer to that of load impedance. Next, what is matched transmission line? What is matched transmission line? When a transmission line is terminated with a characteristic impedance, then the line is called as perfectly matched transmission line. So here the condition is to get the maximum power transmitted, and to avoid the reflections, then we use here impedance matching. Means to get the impedance matching, we use when a transmission line is terminated with characteristic impedance. That is, line is means when the load impedance and the characteristic impedance are same, then the line is said to be properly matched. If ZL is not equal to Z0 case, reflection occur. Okay. So what is matched transmission line means? When a transmission line is terminated with a characteristic impedance, means when the load impedance of a transmission line is terminated with a characteristic impedance of the transmission line, then that is said to be perfectly matched transmission line. Condition is given by here, ZL is equal to Z0. So with ZL is equal to Z0, the maximum amount of energy or power need to be transferred, and reflections need to be avoided. Then define reflection coefficient. So reflection coefficient is the ratio of the reflected wave voltage to the incident wave voltage. So generally it is defined with considered to be as a notation as gamma, and it is defined as the ratio of reflected wave voltage VR to the incident wave voltage as VI. Okay. Sometimes we used to consider it as maximum amount of reflected voltage to the minimum amount of incident wave voltage. That is, V max to the V minimum is given as sometimes reflection coefficient also. The reflection coefficient is the ratio of the reflected wave voltage to the incident wave voltage, right? So if we consider, see, VR by VI means that is given by here gamma in terms of standing wave ratios, that is S minus 1 by S plus 1. Okay, so where gamma is said to be reflection coefficient and S be the standing wave ratio. So to get the equation for this reflection coefficient, we need to use standing wave ratio ranges also. That is, as we know that reflection coefficient gamma is ranging from 0 to 1 and the standing wave ratio S is ranging from 1 to infinity. Right? To define this reflection coefficient, it is the ratio of the reflected wave voltage to the incident wave voltage. Okay. Similarly, a matched transmission line case, when the characteristic impedance of a transmission line is matched with load impedance of a transmission line case, then the line is said to be properly terminated or perfectly matched line. If ZL is not equal to Z0, means load impedance of a transmission line is not equal to the characteristic impedance of a transmission line case, then that particular case we may get reflections, right? To avoid reflections and to get the maximum power need to be transferred in case we use impedance matching. Next is, what is standing wave? Define VSWR. So VSWR, voltage standing wave ratio. Depending upon this standing wave ratio, if you are going to define with respect to voltages, there is a term called VSWR, or if you're going to consider with respect to the currents, then the term is called as current standing wave ratio, that is represented with CSWR. Okay, what is standing wave? So if there is an impedance mismatch on a transmission line, reflected waves are formed and these are combined with the incident waves, then form a standing wave. See, if we consider there is a boundary between medium 1 and medium 2, then in this case, if you consider when the incident wave touches the boundary, part of this incident wave is reflected back to the same and part of this will be transmitted to the next. So depending upon this is the case, standing waves case, there is no reflection. Sorry, there is no transmitted waves. Means if this is the case, the entire incident wave is again reflected back to the same medium. Reflected back to the same medium. Means in the medium one, we have two traveling waves are exist. Those are, one is incident wave and the other one is reflected wave. So the combination of two traveling waves, those are incident wave and reflected waves, are collectively called as standing wave. So voltage standing wave ratio is the ratio of maximum voltage to the minimum voltage in a standing wave, right? So maximum voltage to the minimum voltage means, suppose if you consider the maximum voltages are represented with, these are all the V max and the line distance is given by, this one is V minimum, then it is the given the voltage standing wave ratio S is to be defined as V maximum to the V minimum, right? So if you want to define with respect to the voltages, then the standing wave ratio is said to be voltage standing wave ratio, and it is given by the maximum of voltage to the minimum of voltage in the standing wave gives us voltage standing wave ratio. Suppose if you want to define this with respect to the current standing wave ratio, then CSWR is given to the by maximum of current to the maximum of minimum of current in the standing voltages is said to be standing wave ratio related to currents, right? So what is standing wave means, if there is an impedance mismatch case, in order to get impedance mismatch in case of a transmission line, reflected waves are formed and these are combined with the incident waves. Means in the medium one, there exist two traveling waves. One is incident and the reflected waves. Means whatever the wave which is touches the boundary or strikes the boundary, that is called incident wave. That incident wave is completely again reflected back to the same medium then it is combined with incident wave, then the two waves are said to be standing waves. So standing waves are the waves that won't travel, but the amplitudes or the strengths of those two will be the same, and the directions in which they are propagating are different. Depending upon that, the standing waves are to be formed. So there are two cases of standing waves are there: voltage standing wave ratio and the current standing wave ratio. In order to define this standing wave ratio S, we must consider here that is the ratio of maximum voltage to the minimum voltage in a standing wave ratio. Suppose if you are talking about currents, then maximum it is the ratio of maximum current to the minimum current is given as current standing wave ratio. Next is, what is Smith chart? So it is a polar plot of the complex reflection coefficient. So the graphical part, with the help of to measure the reflection coefficient and load impedances, then standing wave ratios, we use one of the graphical part or polar plot of the reflection coefficient, and it is said to be Smith chart, right? So it is a polar plot of the complex reflection coefficient. Means generally this gamma is expressed as a complex in nature, means it has a real term and an imaginary term, and we should express this Smith chart in terms of polar plot, means it will have the magnitude as modulus of gamma and the phase function as e power j phi. So it is a polar plot of complex reflection coefficient. This polar form magnitude is represented with r and the phase angle is represented with the theta, right? So it is a polar plot of the complex reflection coefficient, and it is the transformation of complex impedance into reflection coefficient plane. With the help of this Smith chart, firstly we'll measure different types of constant resistance circles as well as constant reactance circles. By combining these two, then it will looks like the exactly a Smith chart, right? So it is a polar plot of the complex reflection coefficient, and it is the transformation of complex impedance into reflection coefficient plane. So theoretically also we'll measure reflection coefficient as well as standing wave ratio, but using some mathematical formulas. But with the help of graphical part, we are going to measure reflection coefficient as well as the standing wave ratios. So to measure this one, we use one graphical plot, and this plot is called as Smith chart, and it is represented in the form of polar form. Means it has some magnitude and the phase angles. In order to represent that magnitude, we use constant resistance circles, and in order to draw that phase angles, we use constant reactance circles. So by combining constant resistance circles as well as constant reactance circles, then it is called as Smith chart. What is pseudo Brewster angle? So this Brewster angle is comes under in the case of there is no reflections in the case of transmission lines. The magnitude reaches a minimum and the phase goes through 90° at an angle known as pseudo Brewster angle, and it is represented with theta b, which is equal to sine inverse of formula epsilon 1 by 2 tau epsilon 1 plus epsilon 2. Okay, so what is the pseudo Brewster angle? This is comes under parallel polarization case of a transmission. Electromagnetic waves propagation characteristics. So it is given by the magnitude, means to define this Brewster angle, the magnitude reaches a minimum and the phase goes to the exactly 90° at an angle known as pseudo Brewster angle, and it is occur in the case of parallel polarization. Yes, right. So in the transmission lines case, we use one of the angle called one of the angles to be measured with respect to this one is called as Brewster angle. So with the help of Smith chart, we used to measure reflection coefficient and standing wave ratios, and with the help of this Brewster angle, we'll be able to measure a minimum and magnitudes as well as 90° exact phase angles need to be measured. Next, What is dispersion of a transmission line? So dispersion means the propagation velocity on the line and is not constant with the frequency. So dispersion of a transmission line means it is given by here propagation velocity of the transmission line and is not constant with the frequency. So in general, a propagation velocity or wave velocity is phase velocity is given by Vp is equal to omega by beta. Where omega be the angular frequency of the wave line and beta be the phase constant of the transmission line. So it means the dispersion means the propagation velocity on the line is not constant with the frequency component. So this is the case. It is given by mathematical equation for that Vp equal to omega by beta. Then after that, diffraction. Define diffraction. Means due to its high frequency signal bends around the edge of the object and tends to make the borders of the lighter is known as diffraction. Right? So what we have learned in this particular UHF transmission lines and some of the applications related to this transmission lines is ultra high frequency range of signals need to be analyzed and different types of how the impedance matching need to be achieved. So to get the impedance matching or in order to get a good impedance matching, we need to avoid we need to consider two conditions. Means first one is to avoid reflections and to get the maximum power transfer, we use impedance matching. So when the impedance matching is to be happened, means the load impedance of the transmission line and the characteristic impedance of the transmission line are same, then that is the case. The line is said to be properly terminated. If ZL is not equal to Z0, ZL is nothing but load impedance and the Z0 be the characteristic impedance of the transmission line, then those two are not equal to case or not same case, then reflections occur. That is the case. Impedance matching is not possible. To get the impedance matching, we use different techniques over there. One is different types of wavelength lines impedance matching. That is quarter wavelength line, half wavelength line, and 8 wavelength lines. Input impedance equations are to be analyzed, and depending upon the stubs, we are going to add at the load end. The two cases of the stub matching techniques are there: single stub matching and double stub matching. And now to avoid the reflections or drawbacks which are exist in the means, the single stub matching technique is applicable for only particular frequencies or fixed frequencies. Now to go for variable frequencies, we used to call or by inserting two stubs nearer to the load, then a type of stub matching is called double stub matching. Then after that, in order to represent reflection coefficient, magnitude as well as the phase angles, we use one of the polar plot called Smith chart. So in order to represent the magnitude, we used to consider resistance circles, and to represent phase angles, we used to consider over there as reactance circles. By combining this resistance and reactance circles, it will become a polar plot looks like exactly Smith chart. With the help of this, we will measure reflection coefficient and standing wave ratio. As we know that the ranges of the reflection coefficient and the standing wave ratios, that reflection coefficient is ranging from 0 to 1 and standing wave ratio is ranging from 1 to infinity. As we know that the mathematical equation for reflection coefficient gamma in terms of standing wave ratio as s minus 1 by s plus 1, and standing wave ratio S in terms of reflection coefficient is 1 plus gamma by 1 minus gamma. Depending upon the ranges, if you substitute the reflection coefficient gamma as 0 to 1, we are going to get the standing wave ratio as 1 to infinity. So like this, different applications need to be analyzed in the theoretical classes of theoretical lectures of electromagnetic waves and transmission lines. The module 5 has UHF transmission lines and applications. As we know that UHF transmission lines means is able to provide ultra high frequency ranges components. Frequency transmission purpose, we use UHF transmission line. Range will be more than that of gigahertz. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.